So in this video, we're going to be finding derivatives of the natural log and the natural exponential function. In a previous video, we looked at a graphical representation of the derivatives of each of these functions. But now it's time to look at the analytical part of that. All right, so if we have a natural log function or a natural exponential function, neither one of these are power functions. Power functions are polynomial functions. They have a base of x and a number exponent. Because these don't have a base of x and a number exponent, we can't apply the power rule for differentiation. Okay, so we have to have a new rule to find the derivatives of each of these. And for each of these functions, okay, it has its own derivative rule or formula. So let's start by looking at the derivative of y equals natural log of x. And you know I like to review notation here and there. So for this one, if I was going to find y prime, I would be bringing in the derivative operator. So the derivative here would become dy dx equals, and graphically we saw the derivative is going to be 1 over x. So what I want you to begin to think about is if you don't have a power function and you're finding the derivative of an Ln function, your answer for the derivative is going to be a fraction that you create with 1 on top, and x, or what we're calling here our u, our inside function, okay, in the denominator. So basically if you have an Ln function, the derivative is a fraction, and in this simple case, 1 is in the numerator and x is in the denominator, or this inside piece. Okay, there's another part of this too that we don't ever really apply, but when we get to the next set of differentiation rules, okay, we'll want to know this. Really, my answer of 1 over x is being multiplied by 1 over the natural log of e. This becomes important when we don't have a natural log function, but we have another function, a log function without a base of e. Okay, so let's look at this. So if I were to simplify this right here, the derivative is just 1 over x. And that's because you'll see here shortly that the natural log of e is equal to, in value, 1. This right here equals 1. So in fact, you're just multiplying by a form of 1. So why do we even do that? Because I want you to see the formula for the other log derivatives later and how it has this kind of multiplier in it. All right, and so what happens when we have not just the parent function natural log of x? What happens when we have a natural log function, okay, but there's more to it than just x? Maybe it's 2x, maybe it's 5x, maybe it's 7x, or maybe it's x squared plus 1 in here. So how do we handle that? Well, here's what we call the natural log of u. That's a u, where u represents another function of x. So we're going to have to apply the chain rule. All right, what happens when we find the derivative of this type of function? Which, I mean, really, come on, we're not going to be finding the derivative of natural log of x all day long. That's kind of boring. You need to add a little more to it. So what's the derivative of a composite natural log function? Well, let's apply the chain rule. Well, the first thing we see is we can't use the power rule. It's an Ln function, so create a fraction. You can put 1 on top, and you're going to put the inside function, or u, in the denominator, times, now u is another function of x, so we're going to multiply by the derivative of u with respect to x. So basically it's the derivative of the inside function. The outside function is Ln. You create a fraction, 1 on the top, u on the bottom, but you go back and multiply by the derivative of the inside. And the other factor is 1 over Ln of e. So if I clean this up, remembering that Ln of e equals in value 1, so in fact you're just multiplying by 1, I have this formula. So this is our formula to find the derivative of a composite Ln function. Okay, depending upon what we're working with, it may be helpful for us to write the derivative of the LNU composite function okay, in this format. Du over dx can just be replaced with u prime. So that's the derivative or the prime of the inside function. So sometimes you'll just hear people say the derivative of ln is u prime over u. I'd probably use this formula if the derivative of my inside function was not a fraction. Because if the derivative is not a fraction, I can just stack it on top of the u. So depending on what we're doing, we'll use one of the two of these forms right here. So let's look at some examples of finding the derivative of some ln functions. All right, so here we have a composite ln function. And again, we can't apply the power rule because this doesn't have a base of x with a number exponent. The first thing you identify is, hey, this is an ln function. And for that function, if it's ln, the derivative rule is u prime over u. All right, so let's first of all identify u. All right, this whole thing is u. So if it helps you to come over here and write it out, u is 2x. U prime, the derivative here is just 2. So if you wanted to go straight to the derivative, y prime equals, create a fraction, u prime over u, 2 over 2x. Of course, it is multiplied by 1 over the ln of e, but again, ln e's value is 1. I just want you to see this a few times, and you'll know why when we look at the other derivatives in future videos. All right, so anyway, clean this up, cancel your 2's, reduce them, I should say. 1 over x is your derivative, which is kind of interesting because that's the same derivative as just the parent function. All right, this is one strategy for finding the derivative, just going straight to the differentiation rule of u prime over u for the ln function. Okay, let me give you strategy 2, and I'll call this 1a, I guess, if that's 1. All right, I want you to keep in mind that it's sometimes helpful to not do any calculus first, but to do some log properties. Sometimes helpful to rewrite this function and then find the derivative later. We've kind of worked with that a little bit with some polynomial functions. So the rewrite on this would be, okay, can I use any of the log properties? And I certainly can because I have a product here. Okay, right here, we've got the factors of 2 and x. So I can apply the product property and break this apart and call y equals natural log of 2 plus natural log of x. And then if I went in to find the derivative of this right here would just be 0, because natural log of 2 is just a number. It's a constant, and the derivative of any constant is 0. And the derivative of ln of x is just 1 over x. Of course, times 1 over ln of e, but we know that value is equal to 1, so it's really just 1 over x. So it's certainly up to you guys on some of these ln functions. Do you want to apply some properties and then find the derivative? Or do you want to get straight to u prime over u as an answer? And I can tell you, when these get more complicated, these ln functions, you're going to want to use properties to find, you want to use properties to break it apart before you find the derivative. All right, let's look at example 2. All right, so we have this function. We want to find its derivative. The first thing you do is you identify it's an ln function. The formula, the rule for finding the derivative of an ln function is u prime over u. The next thing in my brain I consider is, would properties help me here in finding the derivative? Would it make my differentiation work easier? Well, I just want you to study this equation right here. I can't apply any of the log properties because I don't have an exponent where it should be to use the power property. I don't have a product, and I don't have a quotient. So I have no choice on this. I have no choice in finding this derivative other than to do u prime over u. This is u. Write that out over here. Find u prime, or du over dx. They're interchangeable. That's 2x. Once you establish that, the prime is just going to be u prime over u, stack it as a fraction, 2x over x squared plus 3. That's the derivative. It may bother you that the ln disappears. It just does. The ln just disappears when you find y prime. That's just part of the process. Okay? The ln is just there to help identify what differentiation rule to use. Once you do, in the derivative answer of an ln function, ln is just gone. Okay, let's look at example 3. All right, so I'm studying this right here. There's no log properties I can use. I mean, I could probably put x back here as an exponent. Well, that's actually going to make it more difficult, I think. I'm hoping that you see that we're going to involve some of our previous differentiation rules with our new differentiation rule here. And I hope you can see this as two variable factors, each with x in it. So this is f, and this is g. Now, I think when you see it that way, when I circle it, you probably conjure up the derivative rule should be product rule. F times g prime plus g times f prime. So I think I'm just going to get straight to the derivative. I don't think I'm going to do the setup here and show all that work, just because the derivative of each of these functions, f and g, by themselves are pretty easy. So the setup isn't really going to help you much. But if you are one that are all in with the setup, then you just go for it. So f times g prime, well, g prime is 1 over x, plus g, left alone, times the derivative of x with respect to x, which is just 1. Well, I have a little bit of algebra I can do. This right here, it's going to clean up to 1. It needs to be there. It doesn't disappear. 1 plus ln of x. So we're combining the product rule with our new differentiation rule of the ln function. Taking a look at example 4, notice where the parentheses are. They're around the log function. Okay, so let me show you some things that this is equivalent to and what it's not equivalent to. And you want to know that because it determines what you do with the problem in finding the derivative. All right, just like trig functions, okay, if I have the power pulled off and I have parentheses around the function like this is equivalent to us putting 3 on the log function. Had it been sine of x inside here, an alternate way to write that would have been sine to the third of x. So these two are equal. Okay, these two are equal right here, but these two are not equal to removing the parentheses and only applying the exponent of 3 onto the x. When you think about order of operations, I have to find the log value first and then cube that log value. Whereas this, you're finding the cube of this x value and then finding the log on that. So those operations wouldn't result in the same answer. So this is the one that's not equivalent to these two that are equal. Had the problem been presented in this format, I would have done like on a trig function and pulled the power off with parentheses. Okay, so we're going to kind of blend a couple of rules that we've learned. Yeah, our new rule is the log rule for differentiation. However, we see this as a composite function. The outside function, so if you wanted to come over here and record your functions, okay, the outside function f would be x cubed, and the inside function would be ln of x. So when you see it as a composite function, remember it's the chain rule. So the derivative of the outside function, drop the 3 in front, reduce the exponent to 2. If you wanted to show the setup, what you're doing is multiplying by the derivative of the inside function, or the derivative of g. All right, for this part right here, you can leave the parentheses as is, or if you wanted to, you could put the square back on the log function with the x here. I wanted to show you that one time, but from now on, I'll likely leave it with the parentheses. All right, and then finding this value is just going to be 1 over x. All right, you're done with the calculus. What we have to do is clean it up, create one fraction, and I'm going to return that square to that power right there to the outside of this parenthesis. And that's your final answer. All right, so let's take a look at example 5. All right, our objective is to find the derivative. So if you were just to jump right in to this problem, notice that it's a ln function, and the derivative of that is going to be u prime over u, and you just jump in and you say, hey, that's u. I just want you to kind of think about how complicated finding this derivative might be. Right, so this is u rewritten with a rational exponent. Okay, but if you looked at u prime, you're going to have to apply the chain rule. And that's going to get kind of complicated. And then times the derivative of the inside, which is just 1. So you'd have to come over here and you'd have to stack u prime over u. I mean, it can be done, but it's just going to be kind of some intense algebra. So this is one where we might want to involve the properties, the log properties. So I might want to first of all rewrite this. Remember, this is not a power function. What students oftentimes try and do is they try and find this derivative using the power rule by putting the 1/2 in front and reducing this exponent. We can't use the power rule on an ln function. The ln function is u prime over u. All right, what I'm going to do is I'm going to do some log properties. Okay, the log properties say with the power here, I can put that in front of the ln. Oops. And it just goes from here to here. I'm not doing a prime. I'm just moving it. Okay, this is going to make our work with differentiation a little bit easier. Because when I go to find this derivative, the 1/2 just kind of is put on hold out front as a constant multiplier. And then I can focus my attention on the ln function. All right, well, think about how we kind of uncomplicated it by using the log properties. Okay, your new u is x plus 1. The exponent was removed, which makes your differentiation, oops, u prime here, a lot easier. And the derivative here is just 1. All right, so coming back and looking at finding this derivative, it's an ln function. The derivative is u prime over u, so that's just 1 over x plus 1. I just combine it and write it as a single fraction. It's not necessary to distribute the 2 inside. I probably wouldn't. And you're done. Okay, one more example. All right, here we have example 6. It's y equals ln of the quantity x times quantity x squared plus 1 squared divided by the cube root of that radicand. All right, so if we're going to do differentiation on this, and I see ln and I immediately think u prime over u, well, think through that for a second and what u is. U is going to be this whole thing right here. If you step outside of the problem to come over here and do this work, meaning you record u and then you come down here and go, okay, let me find u prime. Well, this is a mess. It's a huge mess. I would have to do the quotient rule with the chain rule, with fractional exponents. Oh no. I'm not doing this derivative this way. So I must be missing something because obviously this problem's not going to be this difficult to find its derivative. Okay, the thing that you're missing is, remember that with ln you want to use the properties when applicable, the log properties from before calculus. All right, so what I'm going to do is I'm going to apply as many properties as I know to this function. It's going to look like I'm going to make it real difficult by breaking it apart, but it actually makes the differentiation a lot easier. All right, so the first thing I see is a quotient. So I'm going to take the natural log of the numerator. And I might want to put that in its own kind of brackets or parentheses. And then minus. And what I'm going to do is in the denominator, I'm going to rewrite that as a 1/3 power. Remember, we're not doing any calculus. This is all before calculus stuff. I have not used every property possible for logs. And so for my differentiation, I want to continue to use as many properties as I can that apply before I find the derivative. All right, and here we have a product. And I also have a power on that factor. So it's natural log of x plus natural log quantity x squared plus 1 squared. And then here I see that I can apply the power property. I'm not doing calculus. I'm not doing the power rule. I'm not pulling the 1/3 in front and having to reduce that exponent by 1 whole. I'm simply moving the power to the front of the log function by using a property from before calculus. There's no more properties that I can apply to this term, so I'm going to come back here. I see I can move the 2 in front here. You might be concerned that you think, man, this is making it a lot more difficult, but in fact it's not. The differentiation, which is next, okay, is going to be made easy because of what we did. Term by term differentiation. So the derivative of natural log of x is just 1/x plus here 2 is just a constant multiplier. So I'm going to actually put 2 on top. This derivative is going to be u prime over u. So it's 2 times u prime. Well, u prime is going to be this derivative, that's your u, over x squared plus 1. I'll come back and make that 4x in a minute. I have to go back to my other color. All right, minus 1/3, that's a fraction. And now this derivative right here is u prime over u. So I'm just going to kind of think about that as u. And then I'm going to kind of extend my fraction here. I had the 1/3 there as a constant multiplier. U prime is 6x squared stacked on top times quantity 2x cubed minus 1. All right, right here I notice I can reduce this 3 with this 6. And it looks ugly, but it sure was easy to find. I'm not going to go through and find a common denominator. That'd be too tedious, too much work, and that's not the intent of this problem. The intent of this problem is, do you see that you should use log properties to break it apart so that the differentiation is made easier? So hopefully you have a better understanding of the ln rule, and the ln rule being just u prime divided by u.